Okay, so where are we? We have been talking about satisfiability problems, right? And in the last class we discussed why satisfiability problems are an important problem to solve, right? And the reason it's an important problem to solve is because it's a canonical NP-complete problem, which basically means you give me a hard problem if it's in the class NP, which a lot of the real world practical problems are, then I can convert it into a SAT problem and I can solve it using SAT. And if I have solved it using SAT, the solution of SAT will give me the solution of the original problem. What is the SAT problem? The SAT problem is a problem where I have some variables, logical variables, and I have a set of clauses that are given to me, or a formula given to me in a conjunctive normal form, right? And my goal is to find assignments to variables such that all the clauses in my CNF are satisfied, right? And now suppose I want to solve this problem, I want to find a solution, and let's say I am starting with a very brute force approach. Then a very brute force approach would be start with all possible models. By the way, this is also called model finding. Why is it called model finding? Because one complete assignment of variables is a model in the language of logic. We have discussed this earlier. Okay. So if I wanted to do a complete brute force approach, my brute force approach would be go over all possible truth assignments and let's see if any one of them makes the formula true, and if any one of them makes the formula true, you return satisfiable and you return that particular assignment, and otherwise you return unsatisfiable. Now if I wanted to implement this, if I have n variables in my SAT formula, how much time will this take? 2 to the power what? 2 to the power 2 to the power n. Okay, why?
For n variables there will be 2 raised to the power different rows.
Wait. For n variables there will be 2 to the power n different rows. What rows are we talking about?
In a
Truth table, right. But in our language, what will we call them? Assignments, complete assignments or models, right? So there will be 2 to the power n complete assignments, and then why would it take another exponential on that? It won't, right? So there are 2 to the power n assignments, and for every assignment it takes me some linear time to check whether the formula is satisfiable or not, right? Okay. So of course we don't want exponential. 2 to the power n is not very good. We don't want an algorithm which is so bad. We want to do better than brute force. And the first observation that we have probably is this SAT formula is nothing but an instance of another problem we have studied earlier, constraint satisfaction. It's a CSP problem. Why? Because my clause is my constraints, my clauses are my constraints, and my variables have true or false values. So it's basically a CSP. So we can do search for SAT formula as we did search for CSPs, backtracking search. And if we did this, we will call it the Davis-Putnam algorithm. Okay, so it's a new name that I am introducing to you. Davis-Putnam, or later it became DPLL algorithm. DPLL stands for the 4 different inventors who worked on this particular algorithm. Davis, Putnam, Loveland and Logemann. And this particular algorithm came in 1960s. Now I use the word invented, and we'll take let's take a brief diversion and just think about, are algorithms invented or discovered? This is actually a very good question. It's a very hard question. It's a philosophical question. I'm not going to answer this question for you. I don't know. But you should ask this question. You should say that this Dijkstra's algorithm or this depth first search algorithm, is this a discovery or it's an invention? Now we know revolver is an invention, and we know that India was a discovery or USA was a discovery. What is so different between a revolver and a place for example, in the context of finding it for the first time? It already existed, right? Now, revolver did not already exist. Did Dijkstra's algorithm already exist? Did Dijkstra's algorithm already exist in the way different from the way revolver existed? What did Dijkstra do? Dijkstra said, okay, if I put together my computational instructions in a very specific way, then I have an algorithm that works. And what did Cole do in a revolver? He says, if I put together this metal and this spring and this everything in a very specific way, it makes this revolver. I don't know the answer to this question. You know, I keep going back and forth. Some algorithms seem so innovative that they feel like inventions. And some algorithms are so obvious that, you know, you give that problem and you will get to that algorithm, that it feels more like a discovery. It's a feeling. I'm not making a scientific argument here. So anyway, I just said that they invented the DPLL algorithm, but you can say discovered. Okay, it's your personal prerogative at this point. But you should ask these questions. You know, you are a computer scientist, a budding computer scientist. These are fundamental philosophical questions about computer science, right? Anyway, coming back, DPLL. So DPLL essentially says, let's do search, right? You check a partial assignment. If it makes the formula false, return false. If it makes the formula true, return true, or choose a variable in the formula. And then you search for that variable equal to 0 and that variable equal to 1, right? So it's basically branching factor is always going to be 2, right? Of course. And let's say we run this very basic DPLL algorithm. So this is a very, very basic algorithm. So what it does, let's say this is my formula, A or B or C or not B or not C, not A or C. I start doing DPLL search. Let's say I pick variable A first. I decide to go false first. Then if I simply run the algorithm that has been given to me, the question is, does this make formula true or false? No, it doesn't make anything right now. So I go B, I branch on B false, then I ask the question, does it make the formula false or true? So far, no, it does not. I keep doing, I branch on C, then I ask the question, does it make the formula true or false? It makes the formula false. I backtrack. Now when I backtrack, I go back to C and I try the value true, then I try the value true for B, and I keep doing this, and this is how the algorithm will work, and finally I will get the first success, and that's where I will stop. So now, of course, this is a backtracking search algorithm because at any point we are only branching on one variable. This is the search space is the space of partial assignments, just like in a CSP, and it's a depth first search style algorithm, right? In particular, backtracking search. So far, so good, but of course, this does not work because it's too simple and takes a long time. So people started improving DPLL, and of course, there are some very obvious things that you can do to improve DPLL. You must have seen it already. So if a clause has already been assigned a true value, you can remove the clause. If a variable has been assigned a value which is negated in the clause, you can remove that variable from the clause, right? So let us shorten the clauses and remove the clauses whenever appropriate, and an empty clause means false, of course. So suppose I had A or B, I set A to false, so then I'm left with B. I set B to false, then I'm left with an empty clause is false, I backtrack. Okay. So the change in the algorithm would be remove clauses that contain a literal that has already been set, and if a formula contains no clauses, then return true. If a formula contains an empty clause, return false, and you shorten clauses containing negative literal, right? So let's take an example. We started with setting A to false. Now as soon as we set A to false, the first clause becomes, this is where I want to start having you put your thinking caps back on, because I'm going to ask you some questions in the next slide. So as soon as I put A to false, I set A to false, the first clause becomes B or C, the second clause becomes not B, and so on and so forth. Fourth clause becomes true, so you can remove it, right? So this is what we do. This is the formula we are left with. Then we branch on B. We branch on B, set B to false, so then we are left with C and not C, right? The middle formula goes away, and then we set C to false, and this is what we are left with. And as soon as we got an empty clause, we say, oh, this is a failure, let's backtrack. Okay. So now this is where we start from, and now we ask the question, can we do better? Right? And because it is a CSP, you sort of know what does better mean. Better means, what will be the notion of better in the context of backtracking search? How can we do better? Detect failures early, exactly. And what else? Choose which variable to branch on, right? So those are the two important levers we have right now. Choose which value to branch on is also appropriate, and we will see an example. So in order to get your intuitions going, let us look at this particular formula. Now if you were looking at this formula, which variable would you pick first? Think about it. Think about it. I will ask a random person. Let's say you have to figure out how to make this formula true, right? Formula true means each individual clause should be set true, right? And each individual clause is a disjunction of variables. So how, let's say I ask the person in the green, what's your name? In the second row. Yes? Mayank. So in this formula, what can you obviously say looking at this formula? If C is false, then? Right. If C is false, then not of C will be true. I agree with this statement. But in the context of this formula, can you say that C has to be false if there is a satisfying assignment? You can't say that? Okay, good question. So claim 1, that for this formula to be true, every assignment should have C false. Claim 2, that's not true. How many believe in claim 1? How many believe in claim 2? Nobody, right? Good. So you figured this out. You figured this, that look, there is a formula, we need to make it true. Every clause has to be made true. There is a clause with just one variable. If I have the clause with just one variable, what is the only way to make it true? By choose the variable value such that that literal becomes true. In this case, C should become false. So now there is no point in branching on A, branching on B. You know exactly some value of a variable. Let us set it right away. And this is called unit literals, and this process is called unit propagation. Unit propagation is like forward checking. In forward checking, what would we say? We would say, what are the remaining values? Let us figure out what are the remaining values. And now we have sort of figured out that C has only one remaining value, which is false. So we just pick that and move on. So now that we have set C to be false, we can always shorten the clauses. So now we are left with not B, A not B, E, and DB. In fact, two clauses got satisfied. Now what can we do? Set B to false. As soon as we set B to false, we have got two other clauses satisfied. We are left with D. Now what can we do? Set D to true. So what did we do? We didn't do any search. We only did inference. We said, and the final answer is B false, C false, D true, A and E can be anything. It doesn't matter. So notice that if I did this, this would actually make my search much better, because at some points I will not be searching at all. I will simply be setting the variables which must be set and move on, and must be set a specific value. So not only am I choosing the variable, I am also choosing the value I need to set. I don't have to even try the other value. Now, similar to this, can you think of some other suggestion? Now, this is a harder one, okay, but let's see if you can think about it. It's even true in this particular formula. Can you think of some other way to branch, or not branch but set a value? to a variable. Okay, so let's ask Ishan. Yes, Ishan. We choose the variable that occur in many number of clauses, but you are responding to which variable should I set, but you are still doing search. You are trying both sides, right? My question is there something else we can do where we don't have to even do search? We can just sort of say that let us set this variable, this value, and we don't even have to backtrack from there. It's a good decision. Like we had a decision where we said C has to be false, there's just no way around it. Is there something else? Okay, let me give you a slightly difficult example, then that might help you move. So let's say this is my formula. Now think about it. If you were doing this, right? Again, you should always think about if you were doing this, what would you do? And very often you will have an insight that you can put it into the AI system. At least in the pre-neural world. In the neural world, this thing is hard. In the deep learning world, this thing is hard. But at least until the pre-neural world, you can say that if you have an insight, you can put it in the algorithm one way or the other. Neural world also allows it, but there are levels of indirection which make it harder. Okay, but anyway, we'll come back to that. So let's say this is the formula I gave you. There is no unit literal here. So you can't pick unit literals. Now can you pick some other variable and a specific value and say this variable, this value should give me a solution and I don't even need to try the other side. Okay, so let's see. Yes, what's your name, new person? Abhay, yes. Okay, so if there is a literal which is of same polarity, okay, you are using terms which are, you are not using the right logic language, but you should say if a literal appear in only that form and not its negated form, right? Then we assign that literal first, we assign that literal true. So Abhay makes a very good observation. For example, in this case we can assign D true. So, you know, Abhay says something very interesting. He says, look, think about D. I have D in the second clause, I have D in the fourth clause. In both of these clauses, D is in the positive form. Do I have not D anywhere? I don't have not D anywhere. I just need to find one satisfying assignment. I don't have to find all satisfying assignments. So, if I set D to be true, I am only helping the clause and not hurting the formula at all. I am helping all those clauses where D shows up, but I am not hurting anything. If I am not hurting anything, there is no reason to try the other value. There may be solutions there. There may be solutions with D set to false. I am not saying that there are no solutions, but we don't care. We just care for one solution. Are you able to see this? So, because D only appears in the positive form, we can set it to true. Now, as soon as we set it to true, two formulas get satisfied. Of course, they don't get simplified, and nothing else gets simplified because they didn't even appear. D didn't even appear in other clauses. What else can you do now? We can set B to false because B also has the same characteristic. These are called pure literals. By the way, if we set B to false, we will be left with E, A and not C. And they will also be pure. You can set anything. So your solution would be B false, D true and let's say A true. These are called pure literals. A symbol that always appears with the same sign, right? And that really helps us in not branching on some variable values and making faster progress in search. Okay. So if a formula is only true when literal L is true, branch immediately on that literal. Those are called unit literals. If L does not appear negated in a formula F, then setting L true preserves satisfiability of F, branch immediately on pure literals. Again, these can be viewed as adding constraint propagation techniques into play. And so my final Davis-Putnam Loveland Logemann algorithm becomes everything that I did earlier, plus if F contains a unit literal or a pure literal, just set it and don't even try the other side and move on. So if you actually do DPLL for real on this particular formula, if you look at this formula carefully, are there any unit literals? No. There is no unit literal because there is no clause of size 1. Are there any pure literals? No. A and not A, B and not B, C and not C, all of them are present. At this point, I cannot set anything obviously. So I have to set a variable true and set a variable false and do search. So I do that search. Let's say I set A false. But then as soon as I set A false, the last formula gets satisfied. Second and third formula have become unit. As soon as they have become unit, you set B false, C false. When you set B false, C false, you get an failure. You backtrack, but you don't have to try C true, you don't have to try B true. You go to A and now you try A true. As soon as you try A true, all the first three formulas get satisfied. You are left with the unit clause C. You set it and you are done. And your solution is A true, C true. So this is my DPLL algorithm for solving satisfiability problems. But now we have to ask the question, is there some place where a heuristic could further improve performance? And you know the answer to that. Where is that heuristic? When there is no unit clause, and when there is no pure literal, what do we have to decide? Which variable to do search over. Okay. Let's go back. In CSPs, we said that which variable do we pick? Do you remember? Most constrained. And our definition of most constrained was the number of remaining values for that variable should be the highest. How many values do we have for any variable here? 2. So that maximum remaining values heuristic is obviously not going to work here. Everything will have 2. So let us think about it again. What do we want? We can use the degree heuristic. The degree heuristic says a variable appearing in more constraints. So in this case, a variable appearing in more clauses. However, there is a secondary insight here. And the secondary insight is that, in typical CSPs, the domains are large and so we don't get there. But in logic, the domains are always of size 2. And we know all the tricks about unit literals, etc. And so we really want to get some clauses become as short as possible quickly so that we can set them to those values and we don't have to do that much search. So a particular branch gets explored extremely fast. Okay. So we sort of intuitively want that variable which is likely to create many unit clauses. That is sort of the intuition of the branching heuristic. Okay. Can you come up with something like this? So we can take for every variable, figure out how many clauses it appears in, correct, and what else? And count the number of other variables appearing in that clause. And for the one that is the least number of the other variables. So that's a reasonable suggestion, and when you try it, you might find that there is some inconsistency or something you need to fix. But the final answer is not very different. The answer is sort of what is called the MOMS heuristic. The most occurrences, which is like degree, in clauses of minimum length. Okay. So if I have clauses of length 2, then pick a variable that has that can reduce the clauses of length 2. If I have clauses only of length 3 or more, then I pick all the clauses of length 3 and then find the most occurrences in those clauses. So the extremely large clauses we don't worry about initially, because there are too many ways to set them to true. A clause is a disjunction at the end of the day. So if I have a large clause, then there are many different ways to typically satisfy it, and so we sort of are interested in the small clauses, and then we say let us pick that variable that appears in more of the smallest clauses. Okay. So this is finally the DPLL algorithm for satisfiability.